Right, we'll continue with coordination chemistry. Last class I have given you all the terminology and different types of classifications related to the metal complex as well as what are the different types of ligands. So today we'll just continue with a few terminology in the beginning. Later I'll give you the list of ligands which are important for the coordination complexes. Continuing with the coordination chemistry terminology. Now here I am taking two different types of ligands. One is thiocyanato, another one is a carbonato. Suppose if I choose thiocyanato, in this case sulfur can be a donor, even nitrogen can be a donor. So sulfur can be a donor, nitrogen can also be a donor, but at any given point of time, only one of the donor atoms will bind to the metal. Both cannot bind at a time. Such ligands we call them as ambidentate ligands. Ambidentate ligands are those ligands which have more than one donor atom, but at any given point of time only one of the donor atom can bind to the metal. I'll give you the definition. This is carbonato. Carbonato has got two potential donors, two oxygens are present. But at a given point of time it can bind with the metal with only one oxygen, or it can also bind with the metal with both the oxygens. Suppose that I am choosing a complex both complexes look alike. In this case you have amines, carbonato and carbonato. Oxidation state of the metal is +3 in both the cases. But if you can look at the coordination number, already 5 amines are there. Every amine is a monodentate. So there are 5 monodentates, and usually the geometry will be octahedra. You will be finding the octahedral geometry. So you already got coordination number 5. Then carbonato might be binding to the metal with only one oxygen. It is binding to the metal with only one oxygen. So in this case carbonato is behaving as a monodentate ligand. It is behaving as a monodentate ligand. If you look at the next complex, cobalt, there are only 4 amines which are monodentate. To get the 6th coordination, this carbonato has to behave as bidentate. It has to behave as bidentate. Now coming to the ligand, what type of ligand is carbonato means? This is a ligand where it has more than one donor atoms, but at any given point of time either it can bind to the metal with only one donor atom, or it may bind to the metal with more than one donor atom. So it can change its denticity, and you call such ligands as flexidentate ligand. These are called as flexidentate ligands. There is a flexibility in its denticity, either it can be mono or it can be bidentate. Suppose if I am choosing EDTA is a hexadentate ligand, but depending on the coordination number it can behave as pentadentate, it can also behave as a tetradentate ligand. It can change its denticity. Such ligands we call them as flexidentate ligands. So just note the points about these two. First you write ambidentate ligand. Ambidentate ligand. It is a ligand with more than one binding sites. It is a ligand with more than one binding sites, but at any given point of time, only one of the donor atoms, only one of the donor atoms binds to the metal. binds to the metal. Example, SCN. In the first case, SCN is behaving as thiocyanate S in the next case it is behaving as thiocyanate N. SCN has two donor atoms, sulfur as well as nitrogen. There are two different namings for it. One you call it as thiocyanate, isothiocyanate, that is one type of naming, or you may call it as thiocyanate S if it is binding with sulfur, thiocyanate N if it is binding with nitrogen. So either you call it as thiocyanate, isothiocyanate, or thiocyanate S, thiocyanate N. Suppose if I ask you about the stability of these complexes, just let us extend this topic. If I ask you stability, this is ambidentate ligand. That ambidentate ligand can bind with sulfur, it can also bind with nitrogen. Which one could be more stable, or is the stability same? Because it is an ambidentate ligand, ligand is not changing, so does stability change or not? Then the answer is stability will change, and that stability depends upon a principle which can be explained on the basis of hard and soft acid base principle. There is a principle called as hard and soft acid base principle. Any metal present in a higher oxidation state is considered to be a hard species. If it is a metal, any metal present in a higher oxidation state is considered to be a hard species. This is a separate topic, HSAB, don't bother. So cobalt 3, which is present in a higher oxidation state, is considered to be a harder acid. I am taking a ligand called as thiocyanate. This is an ambidentate ligand which has sulfur as well as nitrogen. Between sulfur and nitrogen, whichever is more electronegative, hardness will be higher for it. So nitrogen has greater electronegativity, therefore we say nitrogen is harder compared to sulfur. This is considered as a base, metal is considered as an acid primarily. So sulfur can bind, nitrogen can bind, but metal is a hard species, therefore it is comfortable to bind with nitrogen rather than sulfur. So that principle we call it as HSAB, hard and soft acid base principle. According to this principle, a hard acid will prefer to bind with a hard base. Soft acid will prefer to bind with a soft base, hard to hard, soft to soft. So in this case, cobalt is hard, sulfur is soft. Cobalt is hard, nitrogen is hard comparatively. So which is more stable means second one has to be more stable. You can just write down that point. According to HSAB, hard and soft acid base, according to HSAB principle, thiocyanate N forms a more stable complex. Thiocyanate N forms a more stable complex. In bracket you can write cobalt 3 is hard acid, cobalt 3 is hard acid, nitrogen is a hard base, nitrogen is a hard base comparatively, so it is only relative term. As such, nitrogen cannot be called as hard. With respect to sulfur, we are calling it as hard. It is a relative term. Next you take down flexidentate ligands. Flexidentate ligands. These are the ligands. These are the ligands which have more than one donor atom, and can change its denticity according to the coordination number, according to the coordination number of the metal. Example, carbonato, sulfato, etc. Carbonato, sulfato, EDTA also can be taken. Carbonato, sulfato, EDTA, etc. So EDTA can exist as EDTA 4 minus, EDTA 3 minus, EDTA 2 minus. Correspondingly, it can behave as hexa or pentadentate or tetradentate. So take down an example of carbonato, show it as monodentate and also as a bidentate. Finished. Next one, chelating ligand. Chelating ligand. Chelating ligand. In classification, we have already seen some ligands which are acyclic. Chela means crab's claw. Just as a crab, it will have its claw and it can easily catch its prey. Likewise, these are the ligands which are just like crab's claw. Whenever a metal comes, it will go and bind with the metal, just as a crab is putting its prey into its claw. So it is the same. Chela means crab's claw. So what type of a ligand is a chelating ligand? We call it as acyclic polydentate ligand. It is not a monodentate. It is a polydentate ligand. Moreover, it is acyclic one. So chelating ligand means it is a acyclic polydentate ligand. What is the importance of this chelating ligand? I am taking a simple example of ethylene diamine. Let me take the complex tris ethylene diamine, cobalt 3. Stability, thermodynamic effects, all these things we have to discuss later. There is separate effect called as chelating effect, which comes under factors influencing the stability. But here, with respect to the different types of ligands, we are studying them. Now just let me compare these two complexes. In one case, it is amine, nitrogen containing donor atom, right? In the second case also it is an amine, but it is like a chelating ligand. This is a polydentate ligand. There is a difference between these two. What is a simple difference? I will just explain now. Point I will not give. Later it can be given. Whatever complex that is being formed, a bond can easily break and again it can remake. Such a process will continuously happen. Whatever coordinate complexes that we have, we always put a reversible arrows most of the times. So the meaning of the reversible arrow means whatever complex that has been formed, at least one of the ligands may break and again it will remake. And such a process is continuous. At room temperature, the energy whatever that is present at 25 degrees Celsius, that thermal energy is enough to break at least one bond, one coordinate bond. So whenever such a bond breaks, suppose if this bond has been broken, that amine will come out, it may go away from the metal. The chances of remaking is difficult because suppose there is a beaker, in that beaker one of the complexes, amine has been broken, it is going away. The chances of coming it back and remaking the bond is little bit difficult. But suppose if I am taking a chelating ligand, it is just like while we go to villages, you go singly, there is a difficulty because you get out in any stop, one will occupy your seat. But if you go with your friend or relative, even if you go out, your friend will save your seat. The same thing will also happen here. Suppose if one of the bonds breaks, that same ligand is still coordinated to the metal by another donor atom, so that if this nitrogen is in the air, it can swing, it can come and remake the bond easily. So this is a theoretical explanation. Also there is a thermodynamic explanation. The number of particles formed will be higher. In case of a chelating ligand, entropy will increase, and due to that stability will also increase. So such type of ligands are called as chelating ligands. Right? So what are chelating ligands means? These are acyclic polydentate ligands, which when bind with the metal will form some cycles. Depending on the number of cycles, the stability of the complex will vary, it will change. Number of cycles are more, stability will increase. Size, this is called as the ring size, and as the ring size is also higher, stability will also increase. That depends on the number of atoms of the ring. It may start from 3, it may go up to 6. That is separately we have to study, but this is called as a chelating ligand. Best example is ethylene diamine. Just write down that point, chelating ligand. It is an acyclic polydentate ligand. It is an acyclic polydentate ligand. Next point, it binds to metal, to form rings. It binds to metal to form rings. Greater the number of rings, greater will be the stability. Greater the number of rings, comma, greater will be the stability. The complex is called chelating complex. The complex is called chelating complex. Chelating complex. This is an important concept because when we go to optical isomerism, these chelating complexes will come, and you have to study about their isomerism also. Optical isomerism, all those things you have to study. You can just take an example of COEN thrice taken 3+. You need not draw this hexamine cobalt, simply you draw COEN taken thrice. Chelating ligands are acyclic ligands. They are polydentate. Previously what we have seen, carbonato, it can behave as monodentate, it can also behave as bidentate. So do you find chelation for a carbonato complex? Suppose if I give you a carbonato, can you expect a chelating complex? Or for a sulfato, can you expect a chelating complex? Answer is yes, you can expect. Supposing that I am taking this cobalt complex, whatever we have taken previously, if the carbonato is acting as a bidentate ligand, then it is forming a chelating complex. This is carbonato. 2 potential binding sites. This is acyclic, it is polydentate, it is flexidentate, it can be monodentate or a polydentate. Suppose if it is acting as a polydentate one, it is forming a ring. And what is the size of the ring means 1, 2, 3, 4, the size of the ring is a smaller one in comparison to this. starting from the metal, whatever atoms that fall within the ring must be counted. That will define the size of the ring. Suppose if I am taking this metal, from this metal this is the ring. How many atoms are falling within the ring? You have to count. 1, nitrogen is within the ring 2, carbon 3, carbon 4, nitrogen 5. So the size of this ring is a 5-membered ring. We call it as a 5-membered ring. How many such 5-membered rings are there? 1, 2 and 3. So greater the number of rings, greater will be the stability. Also the stability depends upon the size of the ring. Now if I compare this with this, 1, 2, 3 and 4, this is a 4-membered ring. A 4-membered ring will be less stable than a 5-membered ring. Okay? That is one more guideline. For chelation, a 4-membered ring will be less stable than a 5-membered ring. Again, if for 5-membered ring, if there is more than one, the stability will increase. You can just write down that example also. Carbonato. In this case, carbonato is acting as bidentate. So it can also act as a chelating ligand. Suddenly a small question may appear, which of the below pairs are flexidentate ligands? Or they may ask which of the below ligands are chelating ligands. If you get carbonato in it, can you put it as a chelating ligand? Definitely yes, because it is a flexidentate one. There is more than one donor atom. It can also behave as a chelating ligand. So carbonato comes under flexidentate, also chelating ligand. Sulfato is also a chelating ligand. EDTA is a chelating ligand. Simply remember, acyclic polydentate ligands come under chelating ligands, acyclic polydentate. Okay. Now let us move to another type of ligand. This is called as a microcyclic ligand. The name itself is indicating that ligand should be cycle. It cannot be acyclic. That ligand should be cyclic. That cycle should be larger enough, macro, not a micro. So there is a simple guideline to remember. For any ligand to be called as a macrocycle, that cycle should contain a minimum of 9 atoms, out of which minimum must be 3 donor atoms. So if at all I am choosing a cycle, that cycle should contain a minimum of 9 atoms and more than that, out of which minimum must be 3 donor atoms. Then I can call it as a microcyclic ligand. A simple example I am taking, these are the 3 oxygens. These 3 oxygens, these are connected by ethylene bridges. We call them as ethylene, though there is no double bond. Common name we call it as ethylene. So what is the size of this ring means? We just count it. Altogether there are 9 atoms, out of which 3 are donor atoms. Since there are 3 donor atoms and 9 atoms altogether, I can call this as a macrocycle. What is the name of this cycle? Generally these are like crowns. These are just like crowns. So the name of the class is called as a crown. We call them as crowns. Whenever the donor atom is oxygen, you call it as a oxa compound or ethers, or you can call them as ethers. So this is a crown compound, which is a ether. At the same time, what are the total number of atoms present in it is 9. So I just put it as 9 hyphen crown. What are the number of donor atoms? 3. I call this macrocycle as 9 crown 3. It is a 9 crown 3. So whenever I compare a macrocyclic ligand with a chelating ligand, what is the difference that you find? I'll just draw it. It is, this is a chelating ligand. In this chelating ligand, it is acyclic. This is an acyclic one, polydentate. This is also polydentate, but it is a cyclic one. Now whenever it is binding to the metal, it is forming some rings. But this, it is already a ring, it is already a cycle, it need not form a cycle again. So between these two, suppose they are going and binding with the metal, which will form a more stable complex, means we always say macrocyclic ligand. What are the reasons for it? Simply I will tell you. Because macrocyclic and cryptate ligands are not part of your syllabus, they are not in the syllabus, only chelating effect has been given. But just let us discuss about that effect also. Suppose this is a acyclic ligand, some donor atom is present. Let me take it as NH2. This is a macrocycle, some donors are present in it. So for this polydentate ligand, whenever it is not bound with the metal, it will enjoy some freedom. We call it as a conformational entropy. The name given is conformational entropy. So whenever it is not bound with the metal, just within the space it is free to move. But whenever a metal comes, it will just go and bind to the metal. It is forming some rings. We call them as chelating rings. This chelating ring will offer stability. But prior to this stability, it was enjoying some freedom. That freedom you call it as a conformational entropy. But whenever it is binding with the metal, it is losing that conformational entropy. Now it cannot freely move because it is a ring. So whenever it is binding to a metal, it has to lose conformational entropy, but it is also gaining some stability by forming some rings. So the stability magnitude is larger. By forming the rings, whatever stability that it is gaining, that magnitude is larger when you compare it with the loss of conformational entropy. There are two magnitudes here. One is loss of conformational entropy, which is like negative. Gaining of stability due to formation of rings is positive. The positive magnitude is more, therefore the stability of a chelating complex is always higher. Now just let me look at a macrocycle. Whenever a macrocycle comes and binds with a metal, it need not lose any conformational entropy because it is already a cycle, it is already a ring, so it need not lose any conformational entropy, and whenever it is coming and binding with the metal, this is also forming some rings. It is just like chelating rings within. So here if it is forming one ring, this is forming 1, 2 and 3, altogether 3 rings are being formed. So which one will be more stable? Definitely a macrocycle will be more stable when I compare it with the analogous monodentate or whatever ligands that you take. Analogous ligands you have to choose. Analogous means if I am taking a macrocycle with oxygen donors, you have to choose a chelating ligands with oxygen donors. If you are taking a macrocycle with nitrogen donors, take a chelating ligand with nitrogen donors, then compare their stability. Okay? So whenever you compare in such a way, always the stability of a macrocyclic metal complex is found to be higher than the corresponding chelating ligand. What are the reasons? First reason, there is no loss of conformational entropy for a macrocycle. Second reason, it is forming more number of rings when you compare it with a chelating ligand. Final reason, whenever nitrogen present in a chelating ligand is forming a bond with the metal, I'll just take one more ligand, you will understand. I am taking diethylene triamine. It is diethylene triamine. I will give you the ligand list, you will come to know. This is called as diethylene triamine. It is binding to the metal from this and from this bond. But this is called as a free end. It is called as a free end. What is that free end? Suppose if this chelating ligand wants to unbind from the metal, where do the unbinding starts? The unbinding starts from here because it is outside. This is outside. Whatever happens, first of all it will happen to the outside, inside is protected always. Likewise, now this is exposed, this is also exposed, it is like inside. It is much more secured. These are called as free end, free ends. Okay? So if I am choosing a chelating ligand, you will be getting some free ends where the breaking can start. But do you find any free end? For a macrocyclic ligand, you don't find any free end. Therefore, still the macrocycle is much more stable because there is no free end. Where will the bond breakage will be initiated? From nowhere. It is difficult for the bond to break. Therefore, a macrocyclic complex is always stable than a corresponding analogous chelating complex. Okay? Just write down a few points. Macrocyclic ligand. For a ligand to be called as a macrocycle, for a ligand to be called as a macrocycle, for a ligand to be called as a macrocycle, comma, there must be a minimum of there must be a minimum of 9 atoms. There must be a minimum of 9 atoms, out of which 3 must be donor atoms. Out of which 3 must be donor atoms. The donor atom could be The donor atom could be oxygen, in bracket you write oxa or ether, nitrogen, bracket aza, sulfur, bracket sulfa, and phosphorus, bracket phospha. The ligands end with A, oxa, aza, sulfa, phospha. Sulfa can also be called as thia. Okay, these are the donor atoms. Next, a macrocycle can form a more stable complex. A macrocycle can form a more stable complex in comparison to its analogous chelating ligand. The reason for higher stability of a macrocyclic ligand are first one, no loss of conformational entropy, no loss of conformational entropy, second one, formation of more number of rings, third, no free ends, in bracket you put breaking point. Free ends are called as breaking points. No free ends. One example you can take 9 crown 3. Next point, the most commonly found crown ethers are 18 crown 6, 18 crown 6, 18 crown 6. It means there are 6 donor atoms. Altogether there will be 18 atoms within the macrocycle. Therefore, you call it as 18 crown 6. It is the most commonly found macrocycle. Write a question. When potassium binds with 18 crown 6, when potassium binds with 18 crown 6, how many chelating rings are formed? When potassium binds with 18 crown 6, how many chelating rings are formed? Yeah, what is the answer? 6. What is the size of each ring? What is the size of each ring? 5-membered. So this is 1 5-membered ring, 2, 3, 4, 5 and 6. Altogether there are 6 5-membered rings. Since there are 5-membered rings, stability will be very high. Altogether 6 5-membered rings are present. 6 5-membered rings are present. Next question. What are the total number of rings? What are the total number of rings in hemoglobin? What are the total number of rings in hemoglobin? How many? 3? 8 total number of rings. Okay, just draw. We are getting a number 4 also. First put 4 nitrogens, make it a part of porphyrins. I mean, these are pyrols. Let us make it a part of porphyrin. Join them with methane bridges. I am not putting all the substitutions. There will be substitutions also. Methyl vinyl, acetates will be present. 2 acetates will be present. That will come in bioinorganic chemistry. This is iron present in the center. Now the question is about how many rings are present, not how many chelating rings are present. Okay, suppose if the question is about how many chelating rings are present, then what is the answer? Whenever it is binding to the metal, then you have to count it as a chelating ring. If the metal is absent, it is not a ring. When the metal is absent, there are 4 rings which are a part of porphyrin. But whenever it is binding to the metal, you are getting 4 chelating rings also. So altogether there are 1, 2, 3 and 4 rings coming from porphyrin, 5, 6, 7 and 8 coming from chelation with the metal. So the answer is altogether there are 8 rings. Altogether there are 8 rings. In these 8 rings, 4 are 5-membered, 4 are 6-membered, but these 6-membered are chelating rings. 4 5-membered, 4 6-membered chelate rings. Size is 6, starting from the metal 1, 2, 3, 4, 5, 6. Finished? The number of rings in iron phthalocyanine, the number of rings in iron phthalocyanine. Iron phthalocyanine. This is iron phthalocyanine. So how many rings altogether? It is 12. Now 1, 2, 3, 4 are also added. But out of these 12, how many are chelating rings? Again 4. The number of rings are 12, but chelating rings are only 4. Write down both. 12. Yeah, the total number of rings are 12, but again the number of chelating rings are only 4. The remaining rings are coming from the ligand itself. This is iron thiocyanine. You also have cobalt thiocyanine. Metal will change. Metal is changing, but the number of rings remain the same. Oxidation state is taken as +2 for the metal, because thiocyanine will be present in -2. Thiocyanine is taken as -2. A question might appear. They may give you iron thiocyanine. Question could be related to how many rings are present, how many chelating rings are present, what is the oxidation state of the metal, what is the coordination number of the metal, what is the geometry of the metal. All these things you can expect. What is the hybridization of the metal? Suppose if I ask you what is the hybridization, it is in a plane, square plane. Square plane means it has to be in a DsP2 hybridization. So hybridization is DsP2. Geometry, square plane, let it be iron thiocyanine or cobalt thiocyanine. These things will work out. Once we move to different theories, valency bond theory, crystal field theory, we have to work out the magnetic moments, crystal field, stabilization energy. There we will choose these examples. We can work out the magnetic properties also. Okay, last example. How many chelating rings are present in bis DMG means dimethyl glyoxymato nickel 2 complex? How many rings are present? How many rings are present? How many rings? One answer is 2. How many? DMG is dimethyl glyoxymato. Dimethyl glyoxymato. This is dimethyl glyoxymato complex. How many rings are present altogether? You can see 4 rings, but how many chelating rings are present? Only 2 chelating rings. This is not considered to be a chelating ring because it is a ring which is formed due to hydrogen bonding. So this is not considered as a chelating ring. There are only 2 chelating rings. But if at all a question comes, what are the total number of rings, then it is 3 and 4 also, but this is not considered as a fullest ring. This is a weak bond. Hydrogen bond is considered as a weak electrostatic force of attraction. So it is not considered as a fullest ring. But suppose in the option there is no 2, there is only 4, then for the number of rings you can go for 4. Okay, write down the last ligand now. Ambidentate, flexidentate, chelate ligand, microcyclic ligand. The last type is cryptate ligand. Cryptate ligand. It is also called as cryptand. Cryptate ligand is also called as cryptand or football ligand or encapsulating ligand. Cryptand, football or encapsulating ligand. it is just considered as a 3-dimensional ligand. If a macrocycle is a 2-dimensional ligand, this is considered as a 3-dimensional ligand. Right. So, what is a cryptate ligand? I am just explaining. This is a 3-dimensional ligand where you have more than one cycle. If you could remember, in the classification of ligands, we have taken acyclic and cyclic. Within the cyclic, we have taken one cycle or more than one cycle. One cycle is an example, macrocycle. More than one cycle, the best examples are cryptands. There is more than one cycle in it, it is almost like a 3-dimensional one. This is a macrocycle. Okay, just imagine that this is a monodentate ligand. It can come and bind with the metal through this donor atom. This is a chelating ligand, right? It is a polydentate ligand. Microcyclic ligand, it is just like a 2-dimensional ligand. Cryptate ligand, it is a 3-dimensional ligand. There is more than one ring. Once the metal atom comes and binds, it will just lock in between. So, the ligand is completely engulfing it, it is completely encapsulating it. It will form a very strong complex, therefore, you call it as encapsulating ligands or football ligands. It is almost like a ball. Once it is coming and binding to the metal, it is forming like a ball, therefore, you call it as a football ligands. So, the highest stability will be with these cryptand ligands only. Next point, nitrogen is a donor atom, oxygens are also donor atoms, but the most common cryptands are, they have nitrogen ends, in between you will be having oxygens, and that nitrogen and oxygen will be connected by ethylene bridges. All these are ethylene only. Mostly found is ethylene. Propylene is also found, but to lesser extent. Ethylene is most commonly found. Okay. Whatever oxygens that are present in between the nitrogens, that must be counted. In this, there is one. Here there is one. Here also there is one. Therefore, we simply call it as 1, 1, 1 cryptand, or simply C111, where C represents a cryptand. I can call it as 111 cryptand or C111. There is also 222, 322, 333. Their stability will vary with metal atoms also. You can just take this example, 111 cryptand. These are the different types of ligands. They will have the highest stability when you compare it with the analogous chelating ligand or a microcyclic ligand or equivalent number of analogous monodentate ligands. Finished. Now, let us write down the list of the ligands. Write the subheading. List of most commonly occurring ligands. List of most commonly occurring ligands. I am taking two tables, you just take one. Three columns. One is ligand, second one is its name, third one is charge. First you start with monodentate negative ligands. First you start with monodentate negative ligands. Monodentate negative ligands. Either I may write it as hydride or hydrido. Both are accepted. Hydride as a normal ligand, hydrido as IUPAC ligand. So simply I can write it as hydride or hydrido, no problem. Charge on the ligand, there is -1 charge. I am just reading them: hydride or hydrido, methyl, phenyl, methoxy, or it could be some alkoxy, aryl, sorry, acyl. This one is acyl. I will write these ligands here. This row completed. NH2 minus, NH2 minus, NH3 minus, N3 minus. This is N3 minus. NH2 minus, NH2 minus, N3 minus. They are correspondingly called as amido, imido, nitrido. N3 minus is called as azido. First row. Nitrito N, nitrito O. Cyno, isocyno. Thiocynato S, thiocynato N, or you may also call it as thiocynato, isothiocinato. Next one is NOS, nitrosyl sulfido. It is bound with N, therefore you call it as nitrosyl sulfido N, nitrosyl sulfido S. This table completed. thiosulfato S, thiosulfato O. You call it as thiosulfato S, thiosulfato O. Next one is sulfido. This one. Next, thiolato mercapto. Just two examples I am taking. Fluoro or fluorido, chloro or chlorido, bromido, iodido. This one. Acetato. Last one is acetato, -1. Cyano-isocyano or cyanato-isocyanato. There you can also put some other atoms if you want. If you want to put selenium, but it is not common one. Instead of OCN, if I put SECN, that would become cyanato, selenocyanato, selenocyanato, isoselenocyanato. So likewise, plenty of ligands will come, but we have to choose the most commonly occurring ligands. All these are the most commonly occurring monodentate negative ligands. Next, you write down some monodentate. Neutral ligands. Since these are neutral, no charge for it. This table completed? No charge for these neutral ligands. Methylamine, dimethylamine. Next one is pyridine. This column, first one is simple phosphine, trifluorophosphine, triphenylphosphine, tricyclohexyl phosphine. It is also abbreviated as PCY3. Simply it is abbreviated as PCY3, tricyclohexyl phosphine. Dimethyl sulfide. All these come under monodentate neutral ligands. Monodentate neutral ligands. Just 2 or 3 monodentate positive ligands. Monodentate positive ligands. NH2 NH3 plus hydrazinium. You can take hydrazine and hydroxylamine for monodentate also. Monodentate neutral, you can simply take hydrazine and hydroxylamine. This is called as nitrocelium or nitrosonium. NO2 plus is called as nitronium. If you take H3O plus, you call it as hydronium. All are having +1 charge. Just these many for monodentate positive: hydronium, hydrogenium, nitroselium or nitrosonium, nitronium. Next, let us take some bidentate negative. Bidentate negative ligand. And I draw it like this. This is dimethyl glyoxymato. If both are OH and OH, you call it as dimethyl glyoxime, HDMG, that is neutral. This is dimethyl glyoxymato, DMG. It has only -1 charge, not 2 minus charges, it has only -1 charge. So in this case, nitrogen is a donor atom, not these oxygens, but nitrogen is a donor atom. Whenever these nitrogens bind, these oxygens just go sideways, and that will form a hydrogen bond. We have seen that hydrogen bond also. Next one is called as biguanidine. This is simply NH. Biguanidine, there is -1 charge. Donor atom can change. Here there could be some derivatives also. Methyls are most commonly found. If this is one donor atom, the other donor atom could be this. So whenever a metal comes, this will shift. This is called as big, simply BIG ligand, biguanidine. Since it is a negative, you call it as a biguanidino. Next one is glycinato. One nitrogen and one oxygen are the donor atoms. Glycinato will carry -1 charge. Two oxygen atoms. -2 charge. This one completed. Next one is catecholato. This is salicylaldehydato. Salicylaldehydato. Hydroxyquinolinato. Nitrogen and oxygen are the donor atoms. Acetyl acetonato. It is simply abbreviated as ACAC. It is called as acetyl acetonato. 2 oxygens are the donor atoms. You can abbreviate it as ACAC ligand. Which one? Charge is catecholato -2, salicylaldehyde -1. This is -1. Finished. Okay, just write down a few. Bidentate, neutral ligands. All these are bidentate negative. Write down some bidentate. Neutral ligands. The most common one. Ethylene diamine. Previously in monodentate neutral, NH3 has come, you have called it as amine, A double M. Here only A single M should come. That was A double M-I-N-E, amine. This is amine. There is a difference. You should not use double M here. You should not use single M there. That is double M. This is called as ethylene diamine, abbreviated as EN. Propylene diamine is abbreviated as PN. Trimethylene diamine, abbreviated as TN. EN, PN and TN. Butylene diamine, BN. Isobutylene diamine, IBN. no charges, these are neutral. All these are neutral, so no charges. To aminopyridine, it is abbreviated as AMP. Next one is bipyridine or dipyridine, abbreviated as bipi or dipi. This is completed. Next one is orthophenanthroline. Orthophenanthroline, it is abbreviated as OPhen. Orthophenanthroline, abbreviated as OPhen. Next one is biguanidine. Previously it was biguanidino, it was negative. Biguanidino is negative, biguanidine is neutral. So there you have taken N minus, but here there will be a hydrogen. Therefore you simply abbreviate it as H big. That one was simply big, BIG. This one is H big. So here usually these two will act as donor atoms. It is just like a flexidentate ligand. There are many potential binding sites, but this is taken as a bidentate ligand. This is completed. This column. Next one is dimethyl glyoxime. Previous one was dimethyl glyoxymeto, O minus. So one negative charge. Here both are OH and OH. Since there is one hydrogen, you simply call it as HDMG. You may just add HDMG. It could be capital DMG or it could be small, but H should be capital. Next two ligands, this is called as diphosphine. Simply it is abbreviated as diphos. The last one is diphenyl phosphinoethane. There are two units. So there are two units, you can simply call it as bis diphenyl phosphinoethane. but simply it is given as diphenyl phosphinoethane, abbreviated as DPPE. Suppose if I am taking methyls here, I call it as dimethyl phosphinoethane, diethyl phosphinoethane, or diphenyl phosphinoethane, dialkyl phosphinoethane. All these are bidentate neutral. Here the phosphorus are the ligands. And just one last one in this. IUPAC names are larger, but you need not put IUPAC name. Simply we use a common name, diarsine. It is still abbreviated as diars. Arsenic is a donor atom here. This column. Finished. Next you put tridentate negative. Tridentate negative. Since these are larger, I am just taking only one table. Charge is -2. Ligand is iminodiacetato, abbreviated as IDA. Iminodiacetato. So you don't find more number of examples as the density is increasing. So just I will be giving only one ligand here. Next for neutral, tridentate. Tridentate neutral. It is abbreviated as terpyridine. It is neutral, so no charge for it. IDA completed. Next one is diethylene triamine. It is abbreviated as DIAN, or you can also call it as DETA. Diethylene triamine. Next for tetradentate negative, usually it is represented as NTA 3 minus. So here itself you are knowing the charge. Altogether there are 3 negative charges, 3 oxygens and 1 nitrogen, tetradentate negative. Tetradentate neutral, tetradentate neutral. There are altogether 1, 2 and 3 ethylenes are present in it. So you call it as triethylene tetramine. It is abbreviated as TRIEN or triethylene tetramine, teta. Triamino, triethylamine, abbreviated as TREN. There is a difference between TRIEN and TREN. TREN is a podal type of ligand. There is a nitrogen, suspended is ethylenes and then amines. So it comes under podal ligand. This comes under linear acyclic, podal. Finished? Just few more ligands, because we mostly get one ligand for the higher density. This is called as cyclam. 4 donors. Next one, pentadentate negative. Altogether there are 3 negative charges. You call it as ethylene diamine triacetate. It is abbreviated as ED3A, ethylene diamine acetate. This is called as ethylene diamine tripropionate, ED3P, ethylene diamine tripropionate. It is a rare ligand. This is done. This is pentadentate negative, 3 negative charges you can put, 3 minus and 3 minus. Then pentadentate neutral, pentadentate neutral. Tetraethylene pentamine, it is abbreviated as tetra-N or TEPA, TEPA, TEPA. Previously for triethylene, please make a correction. I think I have drawn it from here. I might have drawn it from here. Please make a correction. It is from the nitrogen. Just make a correction. I have drawn it like this. Please make a correction. From the nitrogen should come the ethylene. Okay. Pentadentate neutral. And lastly, hexadentate negative ligand. Ethylene diamine tetraacetate. 4 negative charges. This is pentaethylene 6 amines hexamine. It is simply abbreviated as penten or PEHA, pentaethylene hexamine. Last one we have already taken this, hexadentate neutral. crown 6. If I choose a cryptane, just I am giving an example of a cryptane, you tell me what is the denticity of this? What is the denticity? 2 nitrogens, 5 oxygens. It is heptadentate. Heptadentate neutral. This is called as 2-to-1 cryptand. You may also have 2-to-2 cryptand. So 2-to-2 cryptand can be taken as octadentate. All those are not needed, just I have given a simple example for it. So these are the list of various ligands that commonly occur in the coordination complexes. Okay. In the next class we will see some examples where we will work out the oxidation state of some complexes along with the coordination number. We will draw some structures. We will try to find out the coordination number as well as oxidation state. Then we will move on to the IUPAC nomenclature. Okay. So that is where your syllabus is beginning, IUPAC nomenclature. We will have a 10 minutes of break, then organic class will continue.